Yes. Okay. Good evening, everyone. So this is the first session on Qiskit, and today, first of all, I will first discuss actually. This is a programming language, as I will discuss with some hands-on, and why this Qiskit environment, this platform is required. That will be first discussed. Actually, we know that in case of that is to solve a problem, we first develop an algorithm, and then the algorithm is implemented with any programming language that you have done in any lab. But these all are classical, actually, that follows classical computing techniques, or whatever the device. Just like I am using currently my laptop, you are using maybe your computer, laptop, or mobile phones. That all are based on CMOS technology, that is complementary MOS, that is metal oxide semiconductor. Metal oxide semiconductor, you know it is CMOS, PMOS, and NMOS. And if anyone that is feel me, that is you can feel free to ask me. You can just directly unmute yourself and then ask me any question, because it is difficult to check the chat box during the presentation. So that this talk, you can see this in the contents here. First of all, I'll discuss some basic points. Then after, actually, I'll spend 10-15 minutes time with these basic things, and then I will move on to hands-on. That is with Qiskit. So I will share the codes. You also run from your end. Okay, so better you that is open your computer or laptop. Okay, what I was saying that your currently whatever your device is there, it is mobile or laptop or say computer. So these are actually based on CMOS technologies. CMOS means complementary, that is PMOS, NMOS, that is both are there. Because why we use CMOS, or why the CMOS technology is more popular than other technologies, because it takes actually less amount of power. Our laptop, that is generally day by day we have developed the devices such that it takes less amount of power, but still these devices even actually some loss of energy is there, that we see in our classical computing technique. In classical computing means whatever that is we are using, that are known as classical. Here we see that it is not, that is from the suppose, for example, given an input, we are getting from an algorithm or from a function, we are getting the output. So from the output, it is not always possible to get the actual output. If suppose there are multiple inputs are there to get a single output, so you cannot find it out. So what is the exact input there? So this is actually reversible technique, irreversible technique rather. In case of irreversible technique, that there is some problems there that I will discuss here, and that is what you can see here. Some sort of there is some amount of energy dissipation is there if 1 bit of memory information is lost. So that is actually not the new thing. It is that these things were discussed, or this research were published around 40-50 years ago. But in case of reversible computation, what is reversible computation? First of all, so number of inputs here same as the number of outputs, and as well as from the output also we can, that is from a for a particular output there is unique input. There cannot be multiple inputs for a single output. This is our reversible computation. That means we can go from input to output and also vice versa, output to input. So in this case, reversible, we know, just like the reversible that we have learned in our physics, that in any reversible process, energy loss is actually zero. So in reversible computations, so today we'll discuss one reversible computation. Example of this is quantum computation. So that is here, theoretically we can say the power loss is zero. Yes. So that is our quantum computing. So which is actually one example of reversible computing. Here, what is quantum computing? This is in this quantum computing, the computation is done with the which actually exploits or utilizes the phenomena of quantum mechanics. The phenomena of quantum mechanics that we will discuss today is superposition. Also, entanglement is there. Just I will briefly tell you. I will discuss with one example also of superposition. So that are some phenomena of quantum mechanics that actually we use in quantum computing. So classical computing, we do not use it, just our simple classical way of computation. That means just for a single, that is suppose one bit, that is or one variable. One variable can be zero, either 0 or 1. This is our classical thing. But quantum is something different. So that is we have to understand first. So this is our quantum computing. And what is quantum algorithm? Quantum algorithm, just unlike classical algorithm, here that is at least one step or one instruction in the quantum algorithm should use the quantum mechanics phenomena. That is either superposition or entanglement, like this. So that is our quantum algorithm. Any classical algorithm available that I have mentioned here that can be implemented with quantum computing. That is the usefulness of quantum computing. Any classical algorithm available today can be implemented with quantum computers. Along with this, we can design new quantum algorithms. Like today I'll discuss Grover's search. You can also see that Shor's factorization algorithm. That are quantum algorithms, or Simon's algorithm. So these are quantum algorithms because in these algorithms, at least one step or one instruction exploits the quantum mechanics phenomena. And these are the importance why we use quantum computing or quantum computing. That is nothing but a reversible computing can be a future technology. Yes, currently it is very much in infant stage. We have to do lots of researches, lots of things to get a that is just like today's classical computer. But you can think that today's classical computer in 2022-23, but if you go back just 60-70 years ago, you can see that it was we used that time vacuum tubes, or then after 10 years or 15 years, we got the personal computers like this. So today it is advanced, but quantum computer is not advanced yet. So this is actually a new thing. And there's a proverb you all know, early birds catches worms. So since it is a new thing, so we have lots of scope also, and that is to contribute in this domain. And also some internship also I will discuss, where we can that is communicate with direct those who are those giants, those who are actually involved in building quantum computers, and like Google. And above all, of course, here also IBM is leading. IBM led that thing, that's CMOS technology. Here also IBM is currently leading here. Okay, you can see why CMOS we do not want to use, or why we think that CMOS technology cannot be, that is, it is almost saturated, because it is our devices are, you can see that our devices are getting chip size getting smaller and smaller. But how small it can be? It cannot be smaller than atom size. So there should be some replacement on one day. So CMOS is actually quite saturated. And if we use quantum computers or quantum algorithms, that we know, those who are from computer science department, they know. Also, I am telling for everyone that there are lots of problems. From electronics also they can relate themselves. There are lots of problems that cannot be solved within polynomial amount of time, that is n power k times. So there are lots of problems that is takes generally exponential amount of time. That is anything, suppose like 2 power n or n factorial, like this. So this algorithm exponential that runs exponential in classical computers, that can be solved in quantum computers within polynomial time. That can be solved, but there's a problem as there. Acha, maybe one question. Yes, traveling salesman, very good. So if we apply dynamic programming, what should be the time complexity? Big O of n squared times 2 power n. That is, of course, exponential. Okay. Now, third one, side channel attack. This is the term I think you did not hear before. This attack is actually hardware attack. That means here side channel, that is whenever any devices or like sensors, the lightweight devices like sensors, that they leak some information, some power dissipation from their power dissipation or voltage information, we get some information that this type of sensors are being used. That is leaking this side channel information, we can get some information about the device. So that can be protected, because if we use quantum computers, I have mentioned at the beginning of our presentation that we okay, I think it will be better for you if I make it full screen, but tell me. Okay, no problem. Yes, if we use quantum devices, so here, since quantum computing is reversible computing, that means theoretically no power loss. In reversible process, we know from our physics, that is, in reversible process, actually no such you can see theoretically no such power loss is possible. So that means if we do not lose any power, that is information loss in terms of power also can be neglected. And no cloning, this is the also most important factor, that no cloning means it just like in classical any variable, suppose a equal to 5, you can copy it, b equal to 5, just like this, but you cannot copy. Whenever I'll discuss some circuits with Qiskit environment, so then I can or it will be easier for you to understand, because that is why we cannot copy. But right now we can that is understand that no cloning property means we cannot, that is here no cloning means no copy is possible or clone is possible. There's no qubit can be copied. If we want to copy the qubit, we have to make some changes in the qubit or in the circuit. That I will also tell you. Okay, so the suppose we want to build a house, so basic building block is the bricks, we can think. So here we need to that is think about the basic building block of, that is, quantum circuit, which is qubit or quantum bit. Yes, 𝓠ᴜᴜ Satra have a question. Yes, you can unmute yourself, you can ask me. I think unmute option is given to all. Yes, no problem. Anything comes to your mind, you can ask me. This is new to everyone, not for you. Yes. You are not. Why we need quantum computers? Just I have mentioned why we need quantum computers. Okay, I am just going back to this again. Here, that is it can be used as a replacement or alternative of current. Today we are using CMOS technology, but it is this domain is saturated, but in the sense that is we do not make some that is saturated. Why saturated? Because we cannot every time every technology is getting improved, but if we cannot improve anything, that is known as saturation of that technology. That means that technology is at the dead end. We have to think about something new. So why other new computing technologies? Quantum computing is much popular, or researchers or scientists are getting actually paying attention to this quantum computing domain, because the algorithms that we can that run in exponential amount of time, that can be solved or that can run in polynomial amount of time in quantum computers. And also Since quantum computing is reversible computing, so no power loss, power dissipation, or you can say theoretically no such power loss is possible. So power consumption is also can be an issue. Another thing is that you cannot copy a qubit. That's why it will be easier for us, actually, us means for the cryptographers, to design some ciphers. But you can see that is someone can copy, some third party can copy whatever you are sending a message to your friend. Someone can track and then copy. Yes, if someone tracks, but they cannot copy any qubit or quantum bit. That's why I was just going to discuss what is qubit. So, but you cannot copy. Just classical bit you can copy, but quantum bit you cannot copy this. That is the advantage here. But why you cannot copy, we need to discuss something more, then it will be understandable. All right. So quantum bit is just, you can see, quantum analog of classical bit. Classical bit, classical way of thinking, that is a variable can be in one of the two states, either 0 or 1. But interestingly, in quantum, it can be 0, it can be 1, or that is any of the state, that is superposition of 0 and 1. That means what? You can see the diagram here. First of all, I will ask you to see the right one. The right side, you can see downward. Suppose downward spin, this is the, say, spin of the electron. Say downward spin is referring to qubit 1, and say upward spin referring to qubit 0, and any other direction actually referring to the combination of 0 and 1. So that can be written like this, as, say, if I just draw in if I just draw in two-dimensional coordinate system. So anything like this, say it is 1 and it is 0. So anything like this. Now, how to represent this? Is actually, say, one state. Okay, it's a quantum state. Now, this is the qubit. This is the qubit. This is the representation of qubit 0 and 1. This representation is known as bracket notation. Bracket notation. So here, what is bra here? Just like you can see, just first bracket, say like this, open close, curly bracket, open close, square bracket, third bracket, open close. Okay, so here open is, so this is open, gate is close. Here, here it is just, okay, 1 minute. This is, I will write this way. So this is bra notation, and this is gate, the close one. Okay. Say this is a state known as, represented any variable, say psi 1 and psi 2. Okay. So in this way it is represented, and this bra notation is actually, it is a row matrix, and it is a column matrix. Say for example 1, 2, 3, whatever. So it cannot be 1, 2, 3 here, so anything like 0, 1 or -1. Also imaginary variable can also be there. So this is like this, and column matrix means like this. This is a column matrix. Okay, K for column matrix. Okay, so in this way it is represented. So say the quantum state is psi, so we will represent this. Say this is theta angle, so it can be cos theta of 0 plus sin theta of 1. Okay, or you can say alpha 0 plus beta 1. Actually, this alpha and beta are the probabilities of occurrence of 0 and 1. So, for example, if you can see that in case of 1, if psi equal to 1, then this alpha part will be 0 and beta part will be 1. And that is why you can see that this also holds, because alpha square, you can see cos theta plus sin square theta, this also holds. So from the knowledge of alpha and beta, so we can find out the probability of occurrence of 0 and 1 here. So that is the beauty of any quantum state. That is known as superposition of state. That is, it is 0, it can be in 0, it can be it can be in 1, it can be in 0, or it can be in any of the two states. And so, for example, also I can give you one example. Say, suppose we are using 3, or first of all take 2 qubit state. So either any classical system, it will be either in 0, 1, 1, 0, 1, 1. So in this case, in quantum, we can get all the 4s parallelly. That's why it is faster. And that is, computation is faster compared to the classical counterpart. So we can parallelly compute all the 4 things: 0, 0, 1, 1, 1, 0, and 1, 1. 0, 0, 0, 1, 1, 0, 1, 1. These things. Okay. So we can go back to this slide again. So how to represent a qubit? So again, this research is going on. In this, we have seen, or we can see this polarization of photon as a popular measure or popular way to get a qubit, and also nuclear spin. Also other things also are the scientists are using. But polarization of photon, that is either that is, you can see in terms of 0 and 1, that is useful in terms of photon, and also nuclear spin that I have just mentioned here, spin up and down, or any other direction that are used. Okay, one thing before starting the quantum gates, we are here. There are 2 things in quantum mechanics and quantum computation. We are here doing the discussion with quantum computation and implementing these quantum algorithms with Qiskit. So these are the some gates, quantum gates. I will just cover it. Here you can see NOT gate. NOT gate is the simplest gate in quantum computation. And it is also, you can see, NOT also, we can see it is useful in classical computation also, because you can see from A0, that is, if A0 is 1, that means we can tell what is the value of A, 0. If A0 is 1, A0 is 0, we can say that A will be 1. That is the NOT gate, and it is reversible NOT gate. And what is C0 gate? C0 gate, you can see the structure like this: A and B, A and B. So here it is A, and it is A XOR B. And remember that in quantum computation, all the operations are actually represented in terms of XOR operation. Okay, so if I actually draw the truth table here for 0, 0, you can see A is just taking the values, but this value, this output, A XOR B, that means you can say that it is a controlled NOT. That means if A equal to 0, it will be simply 0. If A equal to 0, A XOR B is what? 0 XOR B. That means it is whatever the value of B, it will be there. So here B is 0, so 0. If B is 1, then it will be 1 when A is 0. But when A equal to 1, then you can see it is why it is controlled. So if B equal to 0, then 1 XOR 0 means 1. That means actually B naught. So that means that's why the name C naught came here. C is controlled. When this is actually control qubit, A is control qubit here. Okay. Okay, next comes this other qubits like CC NOT gates. Here, this is also known as Toffoli gate, also very much useful. Here you can see any circuit, and you can see AB, both are control NOT gates. That's why CC, two control NOT gates are there. Okay, and another thing, Fredkin gate. That Fredkin gate can be useful to implement this single Fredkin gate can be useful to implement a 2x1 multiplexer. If we write here in place of A, B, and C, that is the inputs S0, S1, okay, and this as C as A, so you can get the values. So we'll not that is discuss the truth table again. These are the properties of XOR that we can get help to design. I have said that because XOR operation is in case of reversible computation, we do the XOR operations. Whatever, suppose A plus B is there, okay, so we have to represent it in terms of XOR operations, or 1 plus A, actually, or 1 plus A, whatever, that should be represented in terms of XOR operations. Or A0 means 1 XOR A, like this. So everything should be represented in terms of XOR. Okay, now just 2 circuits I will just discuss to save our time. Here is half adder and full adder. Half adder, you know that is sum equal to A XOR B and carry equal to AB. So how we are getting this? I will draw this here. A, B, and another. This is known as, I am just marking here. Okay. Okay. So here, this is which is 0 here, is known as an additional input, known as ancilla. So this is our ancilla. Ancilla input. Ancilla means additional, because this was not there in the half adder. So this 0 is required because we have to get carry as AB. Okay. So how we are getting it AB? You can see this is CC NOT gate. So what is the value here? AB XOR 0. That means whatever the value, that is anything XOR with 0 is that variable. So here AB it will be, and here it is just like A XOR B, which is our sum, and it is our carry. So in this way, I will ask you to that is, you can do it later, that this sum for full adder and this carry for full adder with this circuit. Okay, one thing I missed, that is here, you know, there are 2 output variables in classical and 2 input variables. One additional is required. Why one additional is required? To get this. But since one additional input is required, we have to use one additional output, because this function, in reversible function, quantum computation, all the computations are reversible. That means for every input there is output, or you can see for any output there is unique input. So for any output there is one unique input, just unlike the classical one. So that's why if there are 3 inputs, we have to get 3 outputs. This is every function, reversible function, is bijective. Okay, so let's do some hands-on session that I will give you the codes here. So you can visit this quantumcomputing.ibm.com/lab. So I will ask you, I'm just giving it in the chat box. Okay, I will open it here. I think you can see the browser here. So you have to sign in. So meanwhile you sign in with your IBM ID. So I am telling you what is Qiskit there. So Qiskit, actually it is developed by IBM. So it is a package in Python. The platform is again Python, and a developer is IBM, and here, what is the usefulness of this Qiskit? So we design the quantum circuits. That is, really we are not building the quantum circuits. That is, we are just doing what? It is an online. That is, you can see we are using browsers. That is an online platform, and just like you use Google Doc or Google Sheet, what do you do? Well, that is, you are using the Google services. Okay, here also you are getting the services of IBM's actual quantum devices that you are using through the browser. So for this, you have to sign in here. So please sign in with yours. That is, I have this with me. So create an IBM ID. So you have to create this. With it will not take too much time. Just give your name, email ID, any Gmail ID, and then you can create it. You can create. I will just open my ID here. Okay, if you have created, then either go to launcher, or you can directly click on new file. Okay. So there are two ways to create a new file. Either you can click on this Python 3 PyKernel. See what it comes. You can see lots of packages are imported here. We have imported, that is quantum circuit or other environments. Okay, that is not required every time, but it will help us. That is, we do not need to think about what the libraries we need to import. That is one thing. Just I am deleting this. I will not require. Also, you can click on, I will suggest this Python 3 PyKernel. Here you can see there is nothing, just a cell, blank cell has come. So you can write here, there. So whatever you need to, that is, you can see we do not need to import too many things. Okay, just a few things I have imported from Qiskit environment. So that we can do here. So I'll just do something draft here for since you are doing for the first time, and I will also paste it in the Zoom chat box so that you can also copy and then paste it to your environment. Okay, say practice. Okay, from Qiskit, import quantum register. So you have to know term by term what is quantum register, what is classical register. I will discuss it at the end. So far it is not required. Okay, execute, sorry, AER. Okay, like this. So what is okay, another thing I need to write. So please copy this thing, or better, I will suggest you, I will write this thing here. I'm giving you entire thing. The Zoom chat box, you can see. Okay, actually, yes, this is the code. I'm giving you the link. IBM Quantum Lab. This is the link. Please sign in there. So you can copy that code and tell me that is whether it is you have got any result. Okay, now go back to there. Okay, so you have to take any, first of all, you have, okay, one thing, first thing here, quantum register. Quantum register does what? In case of classical computation, a register stores some bits, some number of bits. Here quantum computation also, quantum register stores some number of qubits here. In place of bits, it stores some qubits. So quantum register. So I will write 2 qubits. Okay. So you may also create for 3 qubits. And say C is classical register. So I will recommend you to use the length of the quantum register and classical register same. Okay. Say the circuit QC, circuit Q, C. Okay. So in this way you can create it. You may save it just using Control S. So this is the basic thing here that we have discussed. Okay, first of all, I will just comment it out. This thing is not will require first. First, we have done this here. 1 qubit we have used, and 1 classical register of the same length, and with this quantum register and classical register, we have created a circuit. So what is circuit here? Circuit is nothing but, so you can see the set of instructions. Okay, just like you can see in Java, class is what? Just a blueprint. The set of instructions are there. So here the circuit is like this. So it is not executable. We'll just provide instructions. For example, we have provided some NOT gate. So simply the circuit say here QCRC dot say X for NOT gate. NOT gates on which bit? Q bit 0. Q of 0. Okay. So we will do this first. Now, after doing this, we have to check whether that is how it is being performing. That is, I have mentioned quantum circuit is a list of instructions. That is, here 1 instruction I have given. We may give more instructions. We can use a Hadamard gate H. So what is Hadamard gate? I will just tell you. So whatever other gates, CC NOT gates we can use, but we cannot right now. We cannot use because it is 1 qubit only. So we can use just NOT gate on this, or we can use identity gate I. It will just make it unchanged identity gate. So how to measure this? What is the value of this qubit? So initially qubit, any qubit by default is 0. So after okay, one question. Can you please zoom the yes? Okay, I'll try. Okay. Just a minute. Here. Is it better? Okay. Okay. Where I was there, yeah. So here. So we are actually applying NOT gate on qubit 0. That means it should be 1. Okay. So we have to measure. So to measure, we will apply that is measure function. In the circuit, there is a function is there measure. So we have to measure this circuit with the actually measure does what? Measure actually maps quantum register to classical register, because here we are doing actually the simulation. We'll be mapping this classical values, register values with the quantum register values with the classical values. Here we will map. That is, you can see here. Just look at here, 2, 2. That means here Q naught or Q0. Q0 is mapped to C0 and Q1 is mapped to C1 correspondingly in this way. So that is done. That is, Q naught value is actually stored into classical register. Okay. Now anything, whatever you can see, it is not any is just a name of any variable. Okay, I am just writing sim for your understanding. So this is the package. AER is the package we have imported. Okay. Now backends, or we may write also AER. I generally use this get backend, get underscore backend. Then, sorry, within quote, any name of the simulator, 𝓠ᴜᴜ simulator we will be using. Lots of simulators available here. First of all, AER. AER is the library or the class, we know, or other classes are there, Terra. So what it does? Actually, it provides us the simulator. Okay. So it has lots of simulator. AER has simulator like state vector, 𝓠ᴜᴜ simulator, matrix state method. Okay. Most popularly, we use 𝓠ᴜᴜ simulator that helps us in our work, but up to 32 qubits. Okay. Yes, you can write any number of qubits more than 32, but 32 qubit in the sense that just like 32-bit processing. That means parallelly 32 qubit you can process maximum with 𝓠ᴜᴜ simulator. If suppose there are 6 qubits and you want to make a superposition of 2 powers, that is 6 qubits. That means 2 power 6. 2 power 6 will superposition means 2 power 6 will be 6 number of qubits will be running parallelly. That is 64 number of qubits. That is not possible with 𝓠ᴜᴜ simulator. Okay. Yeah. So that's why it is better I write this get backend. Okay. So you can do it. Now, after getting this simulator, which is 𝓠ᴜᴜ simulator, will be here. I have to change the name. SIM simulator. We have to run it because again I repeat, this circuit actually set of instructions just like class in Java. Now you have to run it. So there are two ways. We can either use this this execute function that we have imported, or we can just directly like simulator.run, which the circuit name, quantum circuit name. Okay. Here I have used sim. Okay. Now these are the actually other ways I have just mentioned. Okay. Now after getting this, after running this, that means why we are running something to get some result. So that is the result. The result function actually gives us the output of this. So which output we want to get? So we want to measure. We want to measure the number of actually what is the value of this qubit. So that value of the qubit is actually obtained by using get counts. So it looks odd to you. So sir, you are saying the value of a qubit is counts. That is multiple times. Yes, multiple times, because this measure functions runs by default 1024 times. We are calling it just once, but internally, while interacting with the quantum computers, real computers, we are actually performing this here online. But in reality, actually, it runs in 1024 times. So counts means it actually gives you the number. So let's check what number it provides. It is the okay. Name 𝓠ᴜᴜ simulator. Yes, something I have not. Okay, yeah, what it shows 𝓠ᴜᴜ simulator. This. Okay, 1 minute. Sorry. Okay. So how to run? Here you can see I have given this cursor. This is the running. Okay, this is the stop. You can see interrupt the kernel. It will stop. And if you want to restart the kernel, suppose your memory is full, you want to restart the kernel. So this is the thing. Or you can, there are things like this from the file, you can save it. And here you can do these operations, and here run operations, view operations, run operations are there. Okay. But it is preferable to use these buttons here. Okay, so here you can see 1024. Can anyone guess why I have written, or why the output is 1024? The circuit is running 1024 times, and every time it just produces 1 as output. So we are measuring the Q0, the output, the value of Q0. So every time it is 1024. But now, if we use Hadamard gate, what is Hadamard gate? Hadamard gate is actually the gate which is used to make the superposition of states. That means what I have mentioned here. Say, for example, for 0 and 1 or 1 qubit. So it is 0, 1 or simultaneously both. So that is done using Hadamard gate, H gate. Okay. And suppose 2 qubit set. So we have to apply Hadamard gates on Q0. You have to apply Hadamard gate on Q1. If it is 3 qubit, so you have to apply Hadamard gate on Q2 also. If it is 3 qubit, then we will get 8 states. So here it is only 2 states possible for 0, that is 1 qubit. So only one Hadamard gate on Q0 will be sufficient. So if we apply Hadamard gate on Q0, initially by default it is 0. So after applying Hadamard gate, it will be in equal state, the state of superposition state 0 and 1. Okay, that you can see here. If we apply Hadamard gate, then run it, you can see almost equal. Okay, equal probability you will get. So there is no bias, just like a tossing a coin. So head and tail. So if you run there is trial this tossing the coin several times. So that is, you can see 50% chance of getting head and 50% chance of getting tail. So it is, that's why it is actually uniform. So here also this is uniform. So here chances of getting 1. Suppose next time again run it and see, you can see the changes here. So not that 0 will be actually just like bias. Suppose we are getting 0 800 times. Not, it will not happen. This is the superposition state. So 0 will get the same opportunity and 1 will also get the same opportunity to occur. Okay. Now if we draw the same circuit, we have applied this same circuit I have written here. Just write the circuit name dot draw. So again, just compile and run. Here, running this, you can see this is Hadamard gate. Okay. So Hadamard gate on which only 1. Suppose I am writing here 2. Okay. So make it 2 also classical register. So apply Hadamard gate on 0. So let's see what happened. Hadamard gate will be applied on Q0 only. You can see only 1 gate is there. And suppose Q circuit, the circuit name dot operation. Say the operation is NOT gate. Q of 0. That is here. Like this. After Hadamard gate, then NOT gate. If we apply NOT gate on 1, like this. I am copying this and giving you in the chat box. Another one also I am giving. The previous, the measure function. Like this. So you can see lots of operations. That is, operations means in terms of gates in internet. So you will try it. No, just again I will show you. You can see the C0 gate. C0 gate, that is C0 with 2 qubits to be given, Q1 and Q0. Okay. So now you can see for actually here control is 1. The first one is for control. You can see this is the dot here. Okay. If we write 0, so it will be, you can understand, just like the diagram you have seen before. Yes. So this is the, if it is 0 is the control. So this is control and this is the target. Q1, 1 is target. Okay. And yeah. So now for 2 qubits, you can see for 2 qubits, same thing I have written. Nothing changed, just 2 Hadamard gates on Q1 and Q0 and Q1. just what I mentioned. But measured, one thing that has been changed here, measure function. That is measuring, that is we are mapping. If we call measure, we are mapping Q0 to Q1, C1, and Q1 to Q0 to C0 and Q1 to C1. But here, that is what here is written. If you just, I am writing here. If you write measure Q circuit dot measure Q comma C, that is Q0 to C0, Q1 to C1. But if you are writing like this, Q1 to C1, that means only that one part is we are measuring. Yes, one thing. That's why I am giving the here. This is the example of 2 qubits. So this is Q0, Q1, Q0, Q1. But while that is printing, so actually it just the reverse. So it will be 1 0, it will print 1 0. So whenever it will print 1 0, actually you have to think that it is nothing but 0 1. If it is printing 1 0, that means 1 0 means 0 1. So 0 1. So you can see that right portion has no change, but the left portion has changed. Left portion is 1 0, but right portion is always unchanged, 0 0. Because right portion is what? Right portion is this. It is 0 1 according to this printed, 1 0 and 0 0 printed, right? So if it is reversed, if we reverse it, 0 1, that means Q0 Q1, and it is the same Q1 Q0 Q1. So this Q0 part is same because we have not mapped, but we have mapped this. Okay, we have mapped Q1 to C1. That's why even if we are applying Hadamard on Q0, that is not reflected on Q0 because we are not measured. Okay, so that's why you need to better to use Q comma C. Okay, there is I have done it the same thing for the 3 qubits, but only 1 qubit is superposed. That is the middle one. 1 0 1 2. So middle one. So middle one, you can see middle one is there. So only middle one is changed. 1 qubit change means 2 states only. Others are remaining 0. But middle one is either it is 1 or middle one is either 0. Okay. Now we have just coin tossing like code. You can see. I will give you the code here. Partial code. First, write this one here. So this is the same thing, right? This is, you all know. Only we have applied Q Hadamard on Q0. Okay, because 1 qubit state, and we have measured this measuring thing also. You all know. Up to this, you all know. We have discussed. I will not discuss it again. Yeah, but the next thing here, heads equal to R of 0 and R of 1. So what does it mean? You can relate. This is nothing but quantum yes, Python. Actually, in Python dictionary we apply here. You can see this is a dictionary. So this is if we write, what is the thing we are printing? Result we are printing. So this actually, this result dot get counts we have stored in a variable R. So this is nothing but dictionary. R is nothing but dictionary. So R of 0. So what's with the values of R? Just you can tell me. If we apply Hadamard gate on Q0, it is a qubit, 1 qubit state. So R can be either 0 some number of times, and R can be 1 also some number of times. So R of 0 is some number. You will get some numbers. Okay. So just like this, I will run it somewhere here. I am running it here. 1 minute. Let me minimize once. Yeah, I'm running it here. Sorry. Print. First of all, you need to call called quantum coin flip. Say 10 rounds. Okay. Then print R. Or say 1 round. First of all, with easy one. Oh. We can write it here. Okay. So that is the thing here. So we are doing this. Here what? R is nothing but 0, 0. Or that means this function. This function is actually get counts function. Or better, I'm just deleting this one. Only that part I'll write. That I have given. So you can just, those who have written on their machine, then they can correlate. Okay. One thing I have written here, flips is 1024. Okay. So R is actually that is R of 0 will be 533 and R of 1 will be 491. I think now you can understand. So that is here, but it will not be same every time. So R of 0 is for this time say 533 and tail is for this time is 491. Okay. So that we are getting, and we are returning this head tail. Just to actually to get practiced with this. So next we can check if head greater than tails, something, whatever. This is actually varies. If we run, suppose for example, for this time, Bob wins. Next time, score different. Oh, sorry. Bob wins. Alice wins now. So it varies. Okay. So you cannot, that is using Hadamard, you cannot determine which one will be there. There is 1 will occur or 0 will occur. That you cannot determine. Okay. Now that is the, what is the advantage that if we apply this superposition technique, this is superposition technique. This is the one technique that I have mentioned as a quantum mechanics phenomenon. The phenomena, one phenomena is superposition, another is just I have mentioned, I will be explaining in brief that entanglement. Today I will be discussing this. Suppose it is a system, so it is a nuclear spin up and down. Okay. So sum is actually say overall combination of these two is 0. Net effect is 0. So whatever the distance may be, say the distance is too large here, spin up and down. So again the system will be 0. That means wherever there, if one state is known, we know the other state. If we know one state is there, one state is up, so other state is 1. So from one state we can determine another state. But that is the thing we can understand. But that I have mentioned, the distance. Distance does not matter. Whatever their distance, that is, we are in say in one city to another city, or one country to another country, or even more. So we can, from one state, from measuring one state, we can measure other state. So that actually confused many scientists. Even Einstein actually called it spooky, this thing. Entanglement, actually still lots of researches are going on. But our focus is here today, superposition. Superposition, again I repeat, that one state can be in multiple states. That is 0, one qubit state, 0 and 1, or combination of 0, 1. Okay, so that comes to this, how we can use this quantum superposition, this phenomenon. So that actually he was, you can see in 1996, we see the one search algorithm, that is Grover search algorithm. In linear search, the time complexity is big of n. That is, in the worst case, all the elements can be in the worst case. That means if the element is at the end, we have to search all the elements. But in case of quantum computation, you can see this can be done with big of root over n. Why root over n? That complexity I will not discuss, but this is, you can see, this is the fastest algorithm so far available. And why actually this is faster? Because n number of states are there. So if n number of qubits are there, so how many states? 2 power n number of states. So that means, say 3 qubits, there will be 8 states. So linear search will take, in the worst case, 8 number of search operations. But here we have said that 3 qubits, if we apply Hadamard gates on the 3 qubits, so all they will be in the superposition state. That means we can process 2 power n number of states simultaneously. That is 8 number of steps. We are not checking. There is one after another. We are doing this simultaneously. Yes, someone is asking, I think. Okay, if you have any question, you can unmute. Okay, so what we need to do here, first of all, say we have to search for, out of this, say for 2 qubits, 0 0 0 1 1 1 1, sorry, 1 0 1 1. So we need to search 1 0. Okay, this is a search element. So we have to design an oracle. There's a function. So for which, this is the oracle function. Say for which this state will be actually, we have to find it out. So whenever we are getting this, say 0 0 is there, so this is actually not the required one. 0 1 is not required one. 1 1 is not required one. So 1 0 is required one. So that state, so right now I am marking it as x0, x1, x2, x3. So this state will be negated. So this state 1 0, say it is what, 2, say it will be -2, for example. So, and we know what is the proper probabilities here. 1024 is the run. Say 25% every all the 4 states will be around this 25%, almost. Okay. So here this state, which actually is for which it matches the search or search key, it will be made negative. So after that, that is, probabilities are like this. Say all are equal. So that negative, this is the, say, the search value. So this is negated. This probability is made negative. So that means, say this is, say, 25%. And say whatever, 1024, 25%, say 250. All are 250. Okay, for example. So it is now -250. Okay. Now we have to amplify this one. So that means our target is to maximize the probability of this 1 0. 1 0 probability actually will, the probability of 1 0 become much greater than other 3 states, the probabilities of other 3 states. So how to do this? Actually, here I'll show you. Just a minute, let me stop share. I will share you how to actually amplify the or maximize the state. I'm resharing my screen. I think you can see. Yes. Okay, I'm enlarging this. Yeah. So this is actually reflection about the average. That is actually done. So in Grover search, 2 things are done. We made the state negative. That is the probability of the state negative. and then we amplify it in the diffusion. There are two steps, oracle and diffusion. Say here average is this, and on the average we reflect each state. So it is here. So this one was largest, you can see. Now this has been smallest. This one was second largest, so this is second smallest. So like this. Okay, yeah, this one also. That what I have said for negative. Okay, so whenever we negate it, so that is negative. So that negative part can be maximum if we that is reflect the average. Average is this, the dotted line. Okay, so that is actually done mathematically and also with gates. So how actually our target is today to actually show you the actual implementation part. Here, first of all, I will show you the oracle, global oracle. Here, loading can be done any. For example, the say any text value is 0101. So how we can that is how the quantum register, corresponding quantum registers can get those values. So 4 bits are 4 classical bits are there. So we have to take 4 qubit register. So we have got that is here n equal to 4. We have the 4 qubit quantum register. Okay, so this is Q0 will have 0 value, Q1 will have 1 value, and Q2 will have 1 value. So how will get it? Using the load input function. That is, for if we get the text equal to 1, then only we'll just apply not get. Initially we know all these are zeros, so whenever we get any 1 value, then we'll just apply the not get simply to load. So now that I am not saying. So this is the application of global search on cryptography to find out the key of a cipher. That I will conclude. But here you can see the oracle. In the oracle, actually, what we do, whatever this the search value, say the R cipher is the search value. Okay, so whenever CX is what control not get. Control not get means whenever whatever the value will in the R cipher that is stored, or we are getting the same value in R ancilla. Suppose R cipher is 0, so after applying C0, R ancilla will also be 0. Say R cipher is corresponding qubit is 1, so R ancilla will also be 1 if we apply C0 get in this way. Again, now text. So we have to apply that is XOR with text and ancilla get. Okay, so this is there is not get. Simply apply not get. Now the main thing that I have said, that is whenever a match is there, we have to negate. So how to check the match is there? That means output. Say the output is what? Output means whatever the search value is. That is whatever you the state you need to find out, and whatever the value we have currently. So we'll match it. If we match, then we'll negate the corresponding state if it matches. So that is there. That is used with controlled topology gate, MCX. That is done. Okay, that is actually here the implementation. That is the implementation for the cipher, and here the diffuser circuit here. In case of diffuser circuit, what actually you do? You apply the qubits. Suppose there are 3 qubits. You apply that Hadamard gate on the 3 qubits. Okay, and what our target is that we have to map that in our whatever. Suppose, for example, one beautiful example I can see I have seen once in one example. That is, you have to lift a very heavy thing in the earth. So it is very heavy. Suppose it is 80 kg in the earth or 100 kg in the earth. Suppose you have mapped your frame of reference to moon. That example, it is not my example, so I have seen it somewhere. So if you transform your reference to somewhere like moon, so it will be something very less than 100. So there you lift it and then again come back to the earth system. So here we will apply Hadamard gate and NOT gate to qubits. Again, you can see, again we are coming back. That is, we are applying the same thing, NOT gate, and then after that Hadamard gate to the same qubits. Okay. So that is we are using here. And these are nothing. These are actually naming these gates. So not so much useful. That is to return this. But here we have to apply this Hadamard and NOT gate, and then we have to apply this in reverse. That will be required. And what is the required of multi-controlled Z gate? Because we need to amplify. Because that is written here, drawn here. So that probability is the negative probability. So you have to amplify this one. Okay, just like the right side. So so that the probability of the state 01, suppose you have to find out the state 01, so that probability should be maximum. So that is there in the Grover search, Grover oracle and Grover diffusion. But in since it is probabilistic, so you can see the sometimes it is to around 250, sometimes it may be 240, like this. So we have to apply this Grover circuit, some number of we have to apply this combination of Grover oracle and diffusion, some number of rounds. So how many rounds it is tested mathematically, that this number of rounds we have to run Grover search. This is our Grover search algorithm. First of all, we need to find out the state and make it negative, and next we have to amplify it. And this number of rounds, so that's why it is big O of root over n, pi by 4 root over n. So that number of rounds we need to carry on this Grover search. And the thing that is why that is first of all, what is used in Grover search? It is we use superposition technique, and most useful, you can see Grover search is mostly useful in recovering the keys. So since it's root over n, that is n power half, so you can see the search, if whatever the search value, which are actually suppose AES is, you can see 256 right now, we can say it is secure. But in whenever quantum computers will come, we cannot say 256 will be secure, because 256 will be reduced to 128 half. So that 256 length will be actually treated as half 128, because root over n means what? Root over n means n by half. So whatever, if I show you 2 power 256 length, so it is 2 power 256, but say n equal to this. So now root over n means 2 power 128. So it will be treated as AES cipher with 128 qubit size. Okay. So that we have discussed here. And these internships are available. You can copy it down here. Also, or you can take snapshot. I will also share the recordings. Mainly this is you will try to get this quantum summer internship. It generally at the end of the every year, September, October, that time it opens. And others also in the that is throughout the year, other internships also happen. That you can that is follow. And but for that you have to practice something, and you have to make that is there should be a test, just like the last two internships, IBM Quantum Education, and the second one also Qiskit Community Advocate intern. That means you need to be Qiskit Quantum Qiskit Advocate. So who can be Qiskit Advocate? That there is an exam there. Yeah, if you practice well that codings in Qiskit, then you can there is a payment is required. But if you apply, that is, if you get if you apply for the test, then if you qualify, then you will be Qiskit Advocate. And in the IBM Qiskit advocate page, you can search over the net. So you can get several students, undergraduate students, postgraduate students also, they are Qiskit advocates. So what are the benefits of this? That you will, of course, you will get some internships, or you can apply for the internship and you will get it, no problem, generally. But above all, if you are advocate, that is as an intern also, you will be directly interacting those experts who are in working in quantum labs in IBM. And also later you can join as a research scientist also. There is some scopes in IBM or at any other institution as scientist or engineer. And but above all, you can work as intern before that. So that is the scope. So for that, we have invited one IBM Qiskit advocate. She will be giving a talk on the day after tomorrow. That is on 20th January, from the same time, 7:30 p.m. So okay, then if you have any question, you can ask me or write in the chat box, and I will give you the attendance link. Okay, actually, 𝓠ᴜᴜᴜ was asking question. That's why I every time it is direct to 𝓠ᴜᴜᴜ Satra. Anyone having question? But if others having any doubt with the coding also, that time I'll be able. Otherwise, actually, most of the times I have given the code to 𝓠ᴜᴜᴜ, except a few. Okay, you can mail me if you have any question, or contact over WhatsApp @IEM.edu.in. So it is within 1 hour time. Of course, it is not understandable. I can understand that it will be difficult for you, but please start this thing if you want to say. Can you please repeat what did you say? Actually, I mistakenly send all the codes, actually last 3 codes to you, not to everyone. That's what I was saying. But no problem. Actually, I shared. I think others can track. The initial code I shared with everyone. These are the references that I have used. And you can see I will name in the chat box just before giving the attendance link. Nielsen. This book is for quantum computation, if you want to learn. And another book, just let me stop sharing here. I'll just give you the name. The name of the book is Introduction to Quantum Algorithms using Qiskit. So that will be helpful for everyone. If you want to learn, there's a hands-on. Actually, the book is based on hands-on. So not book, you can see it's a tutorial thing. It was published in around 4 years back. So that is that you can follow. The last one, Nielsen is there, of course, but the second one you can follow. You can download it. It is available over internet. Okay. So let me share the attendance here. If you have any doubt or any suggestion that we can do this for this quantum computation or anything else. Attendance link was there. Yes, you can find it here. Okay, not only for the attendance, any suggestion, anything. This is a new thing. I tried, that is from the scratch I started as much as possible. But that is, I just ended where, actually, where that is, I ended global search actually. So from where lots of research activity, recent research activities you can see. Lots of, literally lots of, but still not so much in terms of other domain. But that's why I'm saying be an early bird so that it will be helpful. And if you are interested in the domain, of course. Okay, then see you on January 20th. So there will be a session by an external from IIT and Dhanbad. Okay. Thank you, dear brother. So I'll be sharing after this event all the information with you. So please also, okay, I'm stopping the record here.